general topic.
Yes, thank you for the introduction. The title is very generic for this type of workshop, so I should probably be a bit more precise. So I will talk about two types of problems: vertex partition problems and vertex deletion problems. And we will obtain these hardness results. This is also kind of nothing special for this talk by looking at all reductions. Okay, so maybe let's start with a concrete problem. We were studying this monopolar recognition problem. It's a graph partition problem where you're giving an undirected graph and you want to partition the vertex set in two parts, A and B, and one part should induce an independent set and the other part should induce a disjoint union of cliques, also called cluster graph. So in this example graph you can do it, right? So the green part, these guys will be in B and they induce a disjoint union of cliques. And the blue part is an independent set. Okay, so when we studied this mainly from an algorithmic point of view, we were looking at the, so this is an NP-hard problem as we will discuss soon. We were looking at parameters such as the number of cliques in this cluster graph B, okay? And we obtained some fixed parameter results. And nowadays, if you come up with an FPT algorithm, you always have to somehow give a good, more or less good lower bound that somehow justifies that what you're doing is not too bad, not too far away from the optimum. So we were wondering about lower bounds for this parameter k. Okay, so what's the thing that you do? You look at the known hardness reduction. And the hardness for this monopolar recognition problem is actually, the proof is by a very general result, which is about partitioning a graph into graphs with two different properties, pi and phi. So we have this pi-phi partitioning problem. The input is a graph. Again, we want to do partition again, and the one side should be in the graph class pi, and the other side should be in the graph class phi. Okay, so in our example, pi is being an independent set, and phi is being a cluster graph. And there's this nice result that if the two properties are hereditary, so closed under the leading vertices, and also closed under disjoint union of graphs, and they are not both being an independent set, and they are not both being a clique, then the problem is NP-hard. Right? So these two things are needed to somehow make sure that two coloring does not become NP-hard, okay? Because this is exactly two coloring, or the recognizing co-bipartite graphs. This property essentially means that the forbidden subgraphs are connected for both properties. And the reduction is actually not too complicated. It relies on the fact that there exist graphs that have a unique partition into the two parts. Okay, so we just looked at this reduction and tried to find whether it gives us something for our problem. And it actually does. So the reduction is from a problem that they called P and Q hypergraph coloring. So you're given hypergraph and you want to color it with two colors, and every edge of the hypergraph should have P vertices of the color A. Right? Exactly P. And the reduction has the nice property that if this is your hypergraph that you get as input, then the output graph has this many edges and vertices also. And we found that this P and Q hypergraph coloring, you can also think of it as positive P and Q set, that this has a tight lower bound for the running time. So just by looking at this, we immediately got this extension, or Farrugia got this without knowing it, that you cannot solve these problems in 2 to the little of n plus m time. Okay? So this was very nice, but also a bit frustrating because there's nothing we had to do actually. Okay, so, but somehow this inspired me to look at these general hardness reductions again. And I looked at a class of problems that's very well studied pi vertex deletion. So I'm giving a graph property pi and an undirected graph, and I can delete at most, the question is whether I can delete at most k vertices from this graph to obtain a graph that belongs to pi. So this includes vertex cover, vertex bipartization, minimum feedback vertex set, a lot of these classic problems. Okay, and there's this very nice classic result by Lewis and Yannakakis that for every hereditary graph property, this problem is NP-hard. And now the aim is pretty clear, I guess. We want to somehow adapt this construction to show also tight running time bounds. And we will assume for now that this graph property pi contains all independent sets. Okay? So what does the reduction look like? The reduction is from vertex cover. We can assume that it's from vertex cover and subcubic graphs. It's not really important. So we're given a graph and we want to know, can we delete at most k vertices such that what remains is an independent set. Okay, and what's the rough idea? I will go a bit more into detail when I show the adaptation. You replace the edges of this vertex cover instance by small gadget graphs, and somehow you make sure that these gadget graphs cannot appear too often in graphs that have this property pi. So you need to do something, you need to delete one of two vertices in this graph. This gives you a graph G star, and then the next step is to add roughly theta of n copies of this graph G star in the reduction. So the question is, does it imply these tight lower bounds that we are looking for? And the answer is almost. So the source problem is good. Even if it's in subcubic graphs, then we have this tight running time lower bound. But adding these theta of n copies is too much, because you get theta of n squared vertices in the instance that we produce. And I suspect that this is, I mean, at the time in the 80s it didn't make a difference, and it makes the proof a bit more elegant. Especially the direction to show that whatever you do for your pi vertex deletion problem gives you a solution for the vertex cover. So the reverse part of the equivalence proof. Okay, so what's the idea of the proof? So if all the forbidden subgraphs of the property are biconnected, then it's actually quite easy. It's a bit more tricky if you have cut vertices. So this is to somehow deal with these cut vertices. Yannakakis introduced this notion of alpha sequence, which is just you look at a graph and some vertex C in this graph, and you just look at the connected components that you get when you delete this vertex, and you order them by size, and then the sequence is just this string that you get, or this tuple that you get after you've ordered them. Okay, and the alpha sequence of the graph is just the smallest sequence in lexicographic order that you get when you try all possibilities for choosing this vertex C. Okay, so in this example, if we choose C like this, then we get a 2, 2. And in this graph, this would also be the correct choice, it would be 3, 2, 1. And what's the use of this alpha sequence? It's if I delete, I glue together these graphs, and if I make sure that I delete for each of these larger connected components at least one vertex, then every connected component that remains must have smaller alpha sequences. So if I start my gadget graph with a graph that has very small alpha sequence, I cannot produce other bad forbidden subgraphs. That's the idea. Okay, so for our construction we need to be slightly more precise, let's say. So I introduced an ordering on the graphs that's basically just based on this lexicographic ordering for the alpha sequence plus tie breaking. So isomorphic graphs are the only ones that have the same order in this position. So this is just to make somehow the choice of the forbidden subgraph that we choose unique in some sense. Okay, and so now how do we choose these forbidden induced subgraphs in our construction? So we take one subgraph H, so this is the forbidden induced subgraph with some connected components. H1 is the one that has this largest value, largest alpha sequence, if you want. And we want to make sure that all other forbidden induced subgraphs contain at least one vertex, one connected component whose gamma value is at least as large as this H1. And also there's none that contains only these H1s as max gamma value graphs, and then less H1 components as this one. Okay? So maybe to be slightly more precise, from these three graphs, I would choose H. Okay? This one has this thing has a larger alpha sequence than these guys, and this one has two of this max alpha with the max gamma value, and this one has only one. Yeah. Okay, so this one is a good choice. Okay, so what does the construction look like? We assume that we reduce from vertex cover with n vertices, and this is my fixed graph H that I use in the construction. So I add 2n copies of these small guys here. Okay, and the idea is just if I delete the vertex cover from this other graph, somehow there will remain a sufficient number of these guys to somehow make sure that in the end I will have to delete this guy, copies of this guy. And I do the same for the small gamma value components. And now I have the situation that I might have more than one with the largest gamma value. Okay, so for all except for the last one, I introduce exactly one copy. Okay, so in this case I have two, so one will get a disjoint copy, and this one will be used to somehow encode the vertex cover instance. So this is my vertex cover graph that I want to, the vertex cover instance that I want to reduce. It's actually not larger than this one in this example, but this is not important. So I will build my gadget based on this. So first I introduce one vertex for each vertex of this G, and the small components are somehow glued to this. And then I use the largest component, a largest component, after deleting this cut vertex, to somehow model the edges, right? So this triangle corresponds to this thing, okay? And now if I have a vertex cover here, I can delete the corresponding vertices here and here. This is where they were. All the connected components that remains have smaller gamma value than what I had before. And I have a solution for the pi vertex deletion problem. So for the other direction, there's actually a small problem with the construction. I'm not sure, does anyone see it already? For the reverse direction of the proof. So let's say my forbidden subgraph is very simple. It's the 2K2. And okay, so this one I just make one disjoint copy, and this one is used for the vertex cover instance. Let's say the vertex cover instance is a triangle. I will take this and okay, I will just build a triangle. And then the best thing to do is actually delete this one, right? So it would tell me that my vertex cover number is 1 for this graph, but it's 2. Okay, so there's one small thing that we have to do, and this is actually just to, so the problem is if this H1 occurs more than once, we might delete the wrong copies. And the solution is to reduce from a more restricted variant of this vertex cover, namely for one where we have large girth. So because if I have large girth, then whatever remains in this from this vertex cover gadget, it doesn't have any cycles. So the number of H1 copies that I can kill is the same as the one that I can delete by removing in the gadget side. Okay, so what this gives us is that for every hereditary graph property that contains all independent sets, we cannot solve the pi vertex deletion problem in 2 to the little of n plus m. And this is true even if the degree is bounded by some constant, let's say. That depends on the forbidden induced subclass. Okay, so what if pi doesn't contain all independent sets? So to exclude 2 to the little of n time algorithms, we can just do the trick of complementing what we have, because every graph either contains all independent sets or all cliques, every graph class. So this is fine, and for 2 to the little of m time algorithms, it doesn't work. We cannot get this bound. And the point is very simple. If it doesn't contain all independent sets, then there's some d times k1 that's forbidden. And there are 2 observations that you need. One is there cannot be many high degree vertices. It's very obvious just from the, what is it called, the handshaking lemma. And we can also include very few of these low degree vertices into the graph that remains. So I can just do brute force basically on both sides, and that's it. Okay, I can do slightly better if the property has the graph property has the additional feature that there's some high degree vertex in this graph. So the best example for this is clique. And you can do basically the same as in this clique algorithm that is, for example, in the exact exponential-time algorithms book by Fedor Fomin and Dieter Kratsch. You branch on low degree vertices and branch brute force on the neighborhood. And if there are no such vertices, then you can just do brute force on the total graph. Okay, so we have slightly better running time for this. And that's actually all I really wanted to say about the results. So for the future, it would be nice to actually have a similar dichotomy or almost similar dichotomy for these vertex partition problems. But the situation seems to be a bit more complicated there because there are some cases that are polynomial time solvable. It's, I think if one property is closed under disjoint union and the other one closed under joins. So it's the complement of something that's closed under disjoint union. Another interesting thing would be to have like more general hardness results for these quasi-hereditary properties. This is a property where you cannot delete all vertices and stay in a property, but there exists one vertex that you can delete. And of course, this includes being connected, so it's not NP-hard for all properties. But it would be nice to have like a very general statement saying, like, if I have a quasi-hereditary property that has also some additional features, then we have a tight lower bound for this. And maybe also to look at this pi vertex deletion problem in graph classes. After Denier's talk, the same thing should work for the planar case, giving you 2 to the little or square root n bounds for vertex deletion problems in planar graphs, because we have this bound for vertex cover. And it would be maybe also nice, at least I like this type of research, to somehow get tighter bounds for the degree constraints. Maybe, so in general, this bound that the degree, the smallest degree where the problem becomes hard is 3 times the maximum degree of all forbidden subgraphs. It's tight, because on vertex cover it's exactly degree 3. That makes the problem hard. But maybe for some other types of properties we can get better bounds. Okay, and that's all.
Thanks a lot. Questions?
What is known about edge deletion?
Edge deletion, there's a recent paper on arXiv that shows a very general lower bounds for edge deletion. I think there are no 2 to the little O of k time algorithm for almost anything that we can think of. But so there's a small difference that the running. So here the lower bounds are for this. Switch it off. So here the bound is like little o of m, which is somehow stronger than this little o of k for the edge deletions, because the number of edge deletions is usually smaller, or smaller if you look at these pies that have all independent sets. And so there's still some way of, I think, improving on the arXiv result, but it's much more technical for edge modification problems.
I think just a remark. I think that this arXiv papers only treats of H3 edge deletion, meaning
like one.
Just removing one induced subgraph.
Ah, okay.
I'm not sure if they are having any more general dichotomy for general properties like for Lewis and Yanakakis result.
Ah, okay.
Yes.
I see.
As far as I remember, but I'm not sure.
Okay, yeah. I haven't checked it out too closely, only the abstract.
I also didn't. More close.
Which paper is this?
This appeared on arXiv, I think, in September or October, and they have complete or almost complete dichotomy for H3 edge deletion, when it's NP complete and when it's exponential.
By theorem bound, then it's easier to do it.
Don't remember.
I will find this paper. I can send it to you.
I think some authors from India, but I don't remember the second. Any more questions or remarks? If it's not the case, then let's thank all the speakers.